in 2 dimensions, and we'll neglect column action. So the degrees of freedom involved here are only the vertical translation and then the angular rotation at the 2 nodes of such a beam. The shape function for that case is shown here, and it's a cubic polynomial. We know that that's exact for beams that have concentrated end loads, and that the true solution for deflection is indeed a cubic polynomial. You can get that from the static version of the beam equilibrium law and integrate it directly and get a cubic. Now, we know this is an approximate formula for shape functions when there's a distributed load in the interior, and that would be our case with the distribution of inertia terms. When you do that integration involving the shape function transpose times the shape function, after sufficient agony, you come up with this matrix. Again, you see that there are diagonal terms that are moderately large. The numerical ones here are stronger on the diagonal than the coupling terms. There's a dimensionality difference now between the translational and rotational forces and moments that are developed, so you get some length scales sprinkled in here. So it's a little hard to say then between the rotational and translational effects which of these is quote bigger. But nevertheless, notice that the matrix is full. That means it's fully populated, and that it's coupled. That not only are the translations, say at one end, going to cause accelerations in translational forces at the other end, but in addition, you're going to get rotations and translations interacting, so that a rotational acceleration at one end of the beam will cause translational forces to occur. Let's do a mental experiment with the beam problem. Let's consider that the left node is accelerated upward with a unit acceleration. Then the acceleration vector is shown here. We write out the reversed effective forces here and make D'Alembert happy. That selectively picks out the first column of the mass matrix times these coefficients. And lo and behold, this unit vertical acceleration here, which would cause the body to accelerate with this kind of a pattern, you know, because it will follow the shape function in terms of the distribution of the acceleration field. And it causes this set of reversed effective forces. Now, and moments. Notice that there are some moments involved here. This is a work equivalent set of reactions to that acceleration, which will do the same amount of work on that displacement and acceleration field as the true distributed set of accelerations and masses would have done. It's a little bit of a mouthful, but this is as good as you can do to model the distribution of the inertia in the problem and to move it out to the nodes. Now, I do have rotational effects this time. This is not rotatory inertia that we spoke about earlier that had to do with neglecting the thickness effect. That had to do with moving masses or their characterization in the thickness direction. We're talking about moving masses in this horizontal direction or the axial direction. Much stronger effect and is substantial even for slender beams. The rotatory inertia is important for thick beams and would have to be handled in other ways. So I dare say that no viewer would have come up with this set of inertia forces if they were to think about it on their own for a short period of time. Ultimately, you'd come up with this same theory, I suppose. One thought that has occurred to me as I discuss the consistent mass matrix and the lumped mass matrix is whether the distinction between those two theories will disappear as the element size gets smaller. Now, we know that when there are rotational effects included, that the moments that are involved have length scales in them, and so there will be a bit of a scale effect present. Let's take the Euler-Bernoulli beam element as our example, and then first take the lumped version shown here, and then take the consistent version shown here. Now, we got pretty used to the lumped case where you only had these masses moved to the endpoints where the nodes are. We didn't get coupling between the ends. That's where these the 0 here and the 0 here come in. And neither did we get any rotational moments involved. Rotational accelerations didn't seem of consequence, nor of rotational moments at the ends. So we have a lot of zeros. But the consistent mass matrix for that same two-noded Euler-Bernoulli beam in the xy plane is shown here, and it has fully populated terms here. Let's do a limiting process as the length of an Euler-Bernoulli beam becomes 0, and we'll compare the lumped mass matrix with the consistent mass matrix. What we'll do is let the length quantity go to 0, but hold the constant out front to be rho AL and not drop it out. What will happen then is that on the consistent mass matrix here, a lot of the coupling terms drop out. All of the rotational quantities disappear, and any coupling between rotational and translational disappears. But the appearance of this non-zero coupling term here and here indicates that for an Euler-Bernoulli beam, that no matter how small it is, with a consistent mass approach, an acceleration upward at one end will indeed cause a reversed effective force down on the other end. The magnitude is less than the local acceleration caused force at the node, which you would expect. You expect the diagonal terms to be larger numerically. Now you can readjust the numbers here. Remember that the lumped mass matrix had a unity here and unity here, whereas the consistent mass matrix now puts some of that force through these coupling terms at the other node. If I did this in a really careful way, basically you'd be taking a limiting case of a non-dimensional set of terms and drive out the higher order terms that way. It's been instructive to look at the forces that result from the consistent mass matrix and the lump mass matrix. Another check that we could do would be on the calculation of kinetic energy, because that's one of the major functions of the mass matrix in most dynamic problems. Kinetic energy for a rigid rod, for instance, can be calculated classically here using the moment of inertia of the rod about its centroid and then the angular rotational speeds. We could get something along the same line just by taking the kinetic energy derived by taking our mass matrix, either lumped or consistent, and then putting on a nodal displacement field here that would be consistent with a rigid body rotation. Now, there's a bit of an approximation here, we know, in that now you've got a distributed velocity field along the length of this body. Can you get a good answer out of that? And you almost couldn't hope to get an exact answer. But what will happen is that the consistent mass matrix in this case gives an exact answer. And I think what it means is that we do a very good job of representing the shape functions that can add up in a way that gives you the exact rigid body mode in question. And so we do have built into our particular set of shape functions the exact solution for a rigid rotation. We know that if it were an elastic deformation that had polynomial degree higher than a cubic, we couldn't do it. But this is just a linear interpolation that we're being asked to do, and indeed we'll get the correct answer with the consistent mass matrix. On the other hand, we get a pretty lousy answer with a single large lumped mass model of this system. Let's look at the finite element model for our spinning bar. We're going to use a single Euler-Bernoulli beam element here. It has the translation at each end, and then it has the rotation at each end as variables. Now, of course, they will then be used to characterize what's going on in the interior of the bar, including that rigid body motion that we're interested in. The green figures show the rotation about the centroid with the resultant vertical velocity at the right end and vertical velocity at the left end. I wanted to show those to give you the sign sense that you get this negative velocity at the left end. And so you get the translational velocity here, you get the rotational velocity, and those are at the left node. Then at the right node you get a positive translational velocity and again the rotational, the angular rotation. And that transposed velocity vector is used here and the original velocity vector here. Here's our consistent mass matrix. You multiply it out. Obviously that doesn't happen in 2 seconds, and then you get this answer, which turns out to be exact. So we're fortunate then that for small displacements, you see, right in the vicinity of this flat bar, our finite element theory does indeed predict the proper kinetic energies for infinitesimal rigid body motions about that position. We can't follow the bar to higher and higher angles. If we really were to think ourselves capable of doing that, we would be fooling ourselves. But for these small displacements, we're okay. Aha, but now let's try our lumped mass friend. How's that matrix going to do? Well, I've exaggerated a bit here about what happens, but the mass from the left half of the beam is agglomerated here at the left end, and that on the right half is put all at the right end. That gives us this lumped mass matrix. The velocities are the same as before on both of these terms. And when you multiply that out, you get a number here with the 1/8 that is 3 times too large. And I think you could have anticipated that when you realize that you are migrating the mass outward. And for this particular velocity field, you're putting the mass out where it has much more of an effect on the kinetic energy. And so this is a contrived case that shows the consistent mass to give the exact kinetic energy and the lump mass to give a really lousy one. But if you took a number of smaller elements, then presumably the two would converge quite nicely. That could be a kind of a nice problem to do after class. For our problem session, I'm going to start with the simple rod element and try to find a consistent mass matrix for it. This is just to be a uniform, two-noded rod element. It only has 2 degrees of freedom, namely the translations in the x direction at the left end and here at the right end. The universal formula for the consistent mass matrix is shown here. In this case, the volume integral is the cross-sectional area of the rod times its differential axial lengths. The shape functions are those simple linear ones that we've mentioned many times, where the first one is a descending line and the second one is an ascending line. This is n versus x from 0 to L. The density and the area of the rod are constant, so they're pulled out of the integral, shown here. And then the shape function matrix appears both in the transposed and the normal form. The integration is just a matter of integrating term by term in the matrix. And when you get done, you get the coefficients here. Now the lump mass matrix would have had a factor 1/2 here and zeros on the off-diagonal terms and 1/2 here. So you can see that some coupling has occurred here, that it's a 2-to-1 ratio then between the local effect and the remote effect. So that if I accelerate the leftmost node with a unit acceleration, I'll get 2 parts of reversed effective force there for every 1 part over here. But definitely a coupled inertial effect. Our next problem fills in a gap in our knowledge. We've seen the consistent mass matrix for an Euler-Bernoulli beam lying in the xy plane. Now we need to look at the same matrix in the xz plane, and it turns out to be different. The thing is that there's a kind of conflict in the sign conventions between the classical beam concepts and then the finite element approach. When you take the xz plane and then the y-coordinate points away from us in that case, I can draw that perhaps with an arrow to show that the feathers of the arrow are showing because the arrow is going away from us. And when you do that, you must use a right-hand rule to come up with these finite element conventions on this beam, that the rotation u2 is going to be, in this view, clockwise, as is u4. Unfortunately, when you normally talk about the slopes of a, say, the centroidal axis of a beam, you'd like to think of a slope as this angle. And so we run into the conflict then that the slope, call it dw dx, is related with a minus sign to the finite element coordinate, and likewise at the right end. So there's a minus sign that appears. The difference in our derivation of the mass matrix this time for the xz plane differs from the past only in the sign on the second and fourth shape functions. I show those in red here, and I show them as red curves below. And their sign sense has just been turned around from the previous problem. In our general formula then for the Mij, we'll see a sign change whenever the shape function n sub I takes an even value for I. You'll get a second sign change whenever the nj takes a value of 2 or 4, in other words, an even value. And so writing it out in component form, such as I've done here, it all has to do with the signs of these shape functions and whether they're the negatives of what they used to be. Well, what happens is these off-diagonal terms now get a changed sign from what they were in the corresponding consistent mass in the xy plane. So I think a lot of people hadn't thought or expected to see a different mass matrix in the 2 different planes that might be used. And so that is a bit of a surprise, but it's a real-world thing that we have to deal with. Let's look at the forces that are generated by a triangle that's accelerating in the x direction with a uniform unit acceleration. We'll look at the reversed effective forces that are generated in a classical sense and then compare with the consistent mass matrix prediction. Here's the unit acceleration to the right. At the centroid, you'd get this reversed effective force to the left. From classical theory, that would be the total mass involved, rho AH, but in the opposite direction of the unit acceleration. So we have the classical answer here to work from. Now let's look at our consistent mass prediction. We'll calculate the reversed effective inertia force with the consistent mass matrix. This is the mass matrix, and here's our proposed uniform acceleration, a unit value at each of the nodes. And we show that below with the accelerations as the blue vectors. Then the reversed effective forces that we get are shown here. And when put in with the proper distribution, we find that you get 4/12ths at each of the three nodes, and that adds up to the proper amount. So the consistent mass matrix does an excellent job of predicting this kind of rigid body motion. Let's stretch our imagination a bit now and use the consistent mass matrix concept for a little more complicated element. Let's take a three-noded Euler-Bernoulli beam element. We'll only consider it in planar flexure, and we'll look at it in the XY plane. So we're not interested in axial vibration or torsional nor out-of-plane flexure. We'll just try to find the mass term M33 that goes with this coordinate direction here. So it's a translation at the center node, and presume the node's at the center point. We'll just write out the symbolic expression for that term M33, and we won't do the actual integration. We have two small problems to overcome in doing this calculation. We're trying to find M33. First of all, we need to find the shape function matrix for a three-noded Euler-Bernoulli beam. And secondly, we need to extract out of the general expression for consistent mass those terms that are needed to just give M33. The general formula is like this. We luck out because the n matrix is degenerate. It really is just a row vector. You can carry the column as a dummy index, as I do here, to show that the product involved is an nki times nkj, but there's really only a single value of k taking a unit value. In other words, I'm borrowing this from what would more normally be a multiplication of some rectangular matrices. But it collapses down, and when you put in the M33 subscripts, you get N3, N3 here, and so now we just need to find that shape function. Let's find the shape function now for N3. It's defined to have zeros in translation at both the left and right ends, and then zero slopes at all three nodes. I'm going to use a trick to find that by using a factor here to give the slope and deflection zeros at the left end, and a factor here to give the same zero slope and deflection at the right end. And that trick is to use a squared quantity to get like a double zero there. At the home node, we want zero slope. So if I propose that that function is just a and cross out the bx, and furthermore I don't need the scale a, just take it to be unity, then I have a scale factor out here on the front. Putting those terms together, we have this form right here, and then using that as our shape function, we just have to find what the constant is, which we normalize by using the deflection at the node in question, and we get this constant. That gives us our shape function, and now we just put that in twice in this integral, and that finishes our problem.